this all happening. So what's fascinating about quantum computing is that there's more than one way to do it, right? There's photonics, there's ion traps, there's topological, there's a bunch of ways.
You've got many different ways to do storage. And similarly, you have many different ways to do quantum computing. We use a modality called neutral atoms. And in neutral atoms, a qubit is a single atom. And one of the beautiful things about having a single atom as a qubit is that you could take 1 billion atoms and they would be perfectly identical. There's no manufacturing variation from atom to atom. Whereas if you are actually manufacturing qubits in silicon or something else, you get into manufacturing variations, which makes life much more difficult to control and calibrate and control errors. If you've seen movies where there's a bank safe and the bank safe has these lasers coming down from the ceiling and the villain is trying, or the hero is trying to evade them. Think about that for our computer. What we have is we take these individual atoms and we trap them in tiny laser beams, almost like the laser beams that come from the ceiling in a bank, of course, in a much, much smaller scale. The atoms, for various reasons, like to find themselves in the center of a beam. So they sort of, if you have a grid of beams coming in from top, you're going to capture, with a little bit of work, you're going to capture an atom in every single beam. Now, these atoms, if they are far away from each other, they're indifferent. If they're close together and you shine a different laser on them from a different direction or a different type of laser, then they can interact, they can entangle, that's how you do the quantum calculation. Now, because the atoms like to be in the center of the beam, when you move the beam, the atoms move with it. So imagine that I have many atoms, each trapped in a beam. I'm simplifying it a little bit, but if you want to have two atoms interact, you just move their beams over, get them to do something, and then you could do something else with them. And so that's the essence of how our computer works. And the other thing is that the system operates at room temperature. It does not need these cryogenic cooling systems. Absolutely, really. After faltering early on, quantum computers fashioned out of individual atoms retake the lead. So these are some of the reasons that many experts, including the author of the science paper, believe that neutral atoms are really the leading modality, the leading way to build truly useful quantum